6.3 is on polynomials and their end behavior. A polynomial is any expression where the variables are not in radicals, where the variables are not on the bottoms of fractions, and where the powers of the variables are whole numbers. The coefficients don't have any bearing on whether or not something is a polynomial. So we're actually going to start by playing a game where we classify the following functions. This is the hottest game in America these days. You've probably heard about it. Is it a polynomial or not? To tell if something is a polynomial, we want to check the variables and check their powers. For this first f of x, this power is a whole number, this power is a whole number, it's x to the first, and that 18 has no power on it at all. This is a polynomial. When I put it over here with polynomials, it's going to spin around, because I did it right. What fun we're having. This has an x to the 7th as a whole power, but because we have this variable on the bottom of a fraction, this actually is not a polynomial. When I spin it around, it's going to say no. It's not a polynomial because the fraction has a variable on the bottom. So this one here clearly is a polynomial. You're probably wondering now, what happens if I put it over here? It just projects it, it bounces it. This is a polynomial because the variable has a whole power, whole number power. It doesn't matter if the variable is a, it could be a or x or anything. Try and get ahead of me at this point if you can. Press pause if you want. This has a variable inside a radical. That makes it not a polynomial. This right here has a variable, I can do this, as a power that isn't a whole number. Since that x is to the 1/2, this is not a polynomial. This last one just looks insane, but if we look at the variables only, the variable has a whole number power, the variable has a whole number power, the variable has a whole number power, and the variable has a whole number power. All the coefficients are nuts. The coefficients are roots, and they're radicals, and they're powers, and they're all these weird things. But this actually is a polynomial, because the powers have normal things going on. Good, fun game. We'll play again sometime. Two of the more important parts of polynomials are the degree and the leading coefficient. The degree is the highest power that's present on the polynomial. The leading coefficient is the coefficient on the term with the highest power. And to be sure to grab the sign. So here's a bunch of examples. We're not going to play a fun game this time, but we can still talk about them. This has a degree. We'll talk about the degrees first, actually. Do the degrees first. This polynomial has a degree of 2. Because the highest power is 2. This polynomial has a degree of 5. This polynomial has a degree of 4. Notice that didn't come first, but that's still the degree. It's the highest power. This has a degree of 3. This actually does not have a degree of 12. It's not a degree of 12 because this isn't a polynomial. It's not a polynomial because of this action. So even though that 5x to the 12th is important and tells me things about it, it still isn't technically a polynomial because of that distinction there. Next we'll talk about the leading coefficient. The leading coefficient is whichever coefficient is on the degree. So in this case the leading coefficient is -2. In this case the leading coefficient is -12. Down here the leading coefficient is this +3. And the leading coefficient here is this +4. The sign is incredibly important. So make sure you hang on to that. But the coefficient doesn't have the variable itself. It's just a number. -2, -12, 3 or 4. Okay. I can tell a bunch of things about polynomials from their degree and from their leading coefficient. The degree tells us how many roots there are, meaning how many x-intercepts there are, or how many imaginary roots there are. A 4th degree polynomial will have 4 roots. It could be 4 real, it could be 2 real, or there could be no real and all imaginary. But no matter what, there's 4 roots. A 6th degree polynomial would have 6 roots. A 35th degree polynomial would have 35 roots. The degree tells us how many potential turns there could be. The way we describe turns is also like a maximum or a minimum. Like here, if I think about driving along this road, I turn once, I turn twice, 3 times, 4 times, 5 times. This thing here has 5 turns on it. 1, 2, 3, 4, 5. We would call this right here a local maximum and a local minimum. And this is the overall maximum. And this is not the overall minimum, but it's a local minimum. And here's a local maximum. A 5th degree polynomial, a 6th degree polynomial has at most 5 turns. It could have 3 turns and it could have 1 turns, but it couldn't have 2 or 4. And so an 11th degree polynomial could have 10, 8, 6, or 2 terms. It couldn't actually have 0 terms. It could have 2. Finally, the leading coefficient and the degree tell us about the end behavior of a polynomial. What end behavior means is what's happening to these arrows. We don't worry about the stuff in between, but we want to see if the graph points up or points down as we go left and right. We'll talk about that for the remainder of our time together. End behavior is what happens to a function as it goes really far towards the right, which is the positive x values, and really far towards the left, which is the negative x values. We are trying to determine if the graph points up or down as it moves left or right. That's basically the game here. There's 4 possibilities depending on if the degree is even or odd, and if the leading coefficient is positive or negative. So if you have an even degree function, that means something like x squared or negative 3x to the 10th plus 5x to the 3rd. If the degree is literally an even number. If the degree is an even number, it's an even degree function, the arrows will always point in the same direction. So I'm going to do this positive leading coefficient first. Suppose this was something like y equals 6x squared. And I'll make that more interesting, actually. Suppose it was like y equals 6x to the 8th minus 3x to the 5th plus 2x squared. Well, since the leading coefficient is positive and this has an even degree, I know that both arrows end up pointing up. In between, I don't really know or care what's going to happen right now. Because what I'm really concerned with is this arrow on the right side will point up, and this arrow on the left side will point up. The way that we write this is we say as x goes to infinity, which means as the graph moves to the right, f of x is also going to infinity. The graph is pointing up. Over here, we would say as x goes to negative infinity, as the graph goes really, really left, f of x is also going to positive infinity. They're both pointing up. If you have a positive leading coefficient with an odd degree, like x to the 7th or x to the 3rd or something, this one points up, and this one points down. And who knows what happens in between. So we would say as x goes to positive infinity, f of x goes to positive infinity, and as x goes to negative infinity, meaning very, very left, as x goes very, very left, f of x goes to negative infinity. Finally, if we have an even degree with a negative leading coefficient, these are both going to point down. I don't really know how or what, but as x goes to negative infinity, f of x goes to negative infinity, and as x goes to positive infinity, f of x goes to negative infinity. And over here for this last one, this one points down, this one points up. Who knows what happens in between? We don't really care right now. As x goes to negative infinity, which means left, f of x is going to go up to positive infinity. And as x goes to positive infinity, which means right, f of x is going to go down to negative infinity. I believe that takes care of it for this video. There's more to discuss, but I think this is a good start. Thanks for watching.